good. All right. Oh, screen's not up. My bad. Welcome to class. everybody. Oh, three of you. Okay. Let's see here. Let's see if I can get my screen working. Here we go. Should be up. Awesome. Fantastic. Okay. So, we're now, oh, okay. Awesome. Welcome, Tropical Greek. Tropical Greek. That's your new name. Let's put some cool streamer music on. All right. Okay. So, for a long time now, we're going to be studying the fundamentals of group theory. And, yes, Greek. Absolutely. And, we have to get comfortable with some basic definitions, and the last definition that we encountered was that of a subgroup, and so we'll be talking about that more here later in the class, this class today. But I kind of want to keep starting with this first little question. So just my students, you should keep asking this question to yourselves repeatedly and kind of track the evolution of your mental inner answer to it. Sometimes you can't state everything perfectly in words because the subject is too big, but I hope that you eventually get to a point where you're like, what's group theory about? I mean, it is what it is. And you know what you mean, and I know what you mean, because we've done lots of exploration together and so on. But you can sort of describe facets of it. So the next answer I'm going to give a new answer today. What's group theory about today? Like, I woke up today, I was like, what's group theory about today for me? Okay, so another answer today. It's the systematic sort of mathematics of the concept of symmetry. We all have an intuition for what symmetry means. Well, intuition is not good enough for math, so we're going to abstract away the concept. Give it a notice the key, some key properties of symmetries. Like symmetries can always be undone. Inverses. You have two symmetries, you can compose them to get a third symmetry of a thing, abstract thing. Yeah. If you do nothing, we'll just give that the name of the trivial identity symmetry. Don't do anything to the shape. Every shape has an identity symmetry. Every concept has an identity symmetry. But the more symmetries a thing has, the more easy it is to hold on to play with. Okay, so systematic mathematics of the concept of symmetry. We've taken symmetry, the concept, and made math out of it. And that's what group theory is. And why do I introduce this now? Because I've shown you these dihedral groups as an example, as a series of examples, dihedral groups. And the way they appeared, their very definition was the symmetry of a perfect triangle, or of a perfect square, or a perfect pentagon, or a perfect hexagon. The symmetries that are only involving rotation and reflections, specifically, to be precise. And but in the beginning, you might feel the sensation that there are two types of groups. There's the ones that are like symmetries of shapes, like dihedral groups. And then you'll be biased towards, some people who like geometry might be biased towards those examples rather than some of the boring examples like Z mod NZ or something, which are more number theoretic. Feels like modular arithmetic. Okay, but there will be one grand principle that declares that every group you encounter will be the symmetries broadly construed of some object in mathematics. So in some sense, every group you ever see is the set of allowable symmetries in some context for some object. So yeah, that's my second answer. It's systematic math of the idea of symmetry. Okay. So anyway, now we go to the what we were actually talking about last time was this concept of a subgroup. Let's do that. Subgroups. All right. Okay. So let's do some quick examples. Other than the trivial subgroup or the non-trivial, let's do some non-trivial examples. In D3, the symmetries of a triangle, of a equilateral triangle, the isometries, the rotations and reflection symmetries, rotations, flips of an equilateral triangle. There are a bunch of subgroups. Okay, so here's a good one. So let's write all the elements in this group. Where we're thinking of the triangle as situated like this, and then in the background we've labeled some of the relevant axes of that's pretty good. That's a pretty good triangle. That's pretty good. Okay, so axis 0, and then I just kind of rotate counterclockwise this axis to get the next axis, which is, I'm just calling this 1, and then this 2. Just labeling them, A, B, C, whatever you want to label them. Okay, there you go. Those are these 3 axes to flip across. And then rotation, when you write an angle, positive angle always in math is counterclockwise. That's a convention we've decided on. Okay, thank you Smash Time Fools for redeeming juggling right in the middle of my only 45 minute lecture. Yeah, very funny. Okay, so here's dihedral group D3. It's got 6 elements. In general, Dn has 2n elements. Okay, so that's a general fact. And I hope you've been playing around in D5, D4, sorry, the symmetries of a square, D5, pentagon. You'll see this pattern, 2n. Okay, so here's a subgroup, H. Example. It's just only the rotations. You can check. You compose a bunch of rotations, you get another rotation. Really, when you rotate by one angle, alpha, and then rotate by an angle beta, whether it's positive or negative angle, you always end up rotating by the total angle alpha plus beta. That's just makes sense. So it's again a rotation, and you just add the angles of rotation. All right, Smash Time, absolutely. Okay, so this is definitely this is kind of clearly a subgroup. And notice that it has 3 elements. 3-element subgroup. Fascinating. Okay. All right. There are a couple others too. There's others. Let's do some other examples. Here's a subgroup. Identity plus just flip plus one of the flips. Okay? That's it. 2 elements. Internally, they're closed under the operation of composition because F naught squared is identity again. Inverse of F naught is itself. There's a 2-element subgroup. 2-element subgroup. and then another one, and then another one. So 2-element subgroups. There are some examples, okay? Notice that we so far have gotten, notice the size of these subgroups, 3 and 2, okay, not bad. So here's something. Try to grow your own subgroup. Try to grow another subgroup. Not on this list. And what you'll find is you will find you have a hard time. Okay, so you'll have a hard time. You'll have a hard time producing anything which is not trivial, meaning the whole group or the identity subgroup, which is silly. Yeah, you'll have a hard time finding anything non-trivial. All right, now here's the basic reason why. Okay, so pretend you just start growing a subgroup by adding a bunch of putting a bunch of elements in some braces. Just start. You got to put identity in there. Maybe you put F0. Okay, fine. Maybe you also decided, this is just an example, maybe you also decided to put R120. Okay? Well, you're not allowed to stop your braces here. To make a subgroup is a delicate matter. If someone ever says they've got a subgroup of a group, you should celebrate with joy. It's like vast conspiracy happened and they had this delicate situation where this subset remained within itself under the group operation, including inverse, and every element had an inverse again in the set and identity and so on. So that is a delicate situation. I want to kind of show you what I mean. Pretend you just tried to do this. This is bad. This is wrong. This is not a subgroup. Because we learned last time that that F0 times R120 was F1. Hold on. Let me see if that's right. R120 first and then F0. Okay. R120 sends this thing there and then F0. Oh no, this is F2. F2. There. Okay, we didn't learn that, but I just did it right now. If you swap the order of the I think R120 circle F0 is F1. Okay, so that's the, so class, check this by contact tracing. All right, so if you wanted to start a subgroup by just taking a couple elements and then saying what else, well, you're going to be forced then to include F2 in there. You're going to be forced to include F1. All right, obviously you're going to be forced to include the square of this element, R240. And it's then you've got the whole group. All right, so go play around in the dihedral groups and get perfect clarity on exactly what all the subgroups are. And you'll find that there's very restricted collections of these things in these dihedral groups, and we've just witnessed all of the non-trivial subgroups. There's the rotation group in there, and then 3 sort of reflection groups, each of order 2. That's all of them. All right, awesome. So are there any questions on that example and the sort of concept of a subgroup in general? Hi folks. Yes, closure is not given. That's right, Galvabar. That's the delicate matter. I don't know if you guys ever grew up with those children's book called, like, if you give a moose a muffin or if you give a mouse a cookie. There were these like fun children's books, which was just like, if you give a mouse a cookie, then it'll ask for blah, 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 blah. Then if you give it that thing, it'll ask for something, and it's just a chain of like if-then statements. It's teaching the transitive property of implication in logic, I guess. No, I'm just a fraud, Baku. I'm a fraud. Okay, next. So that was a specific example to get you feeling what a subgroup looks like in nature. Keep the classic example of the set of rotations only among all symmetries of a perfect shape, a perfect pentagon, hexagon, septagon, or whatever, n-gon in general. My name is BMP. All right, next. So let's do some abstract garbage now. Let's switch to some abstract stuff, because this class is abstract algebra. Let's do abstract garbage. So it's good to know, in total generality, for arbitrary group that you ever encounter, what are some of the sort of intrinsic subgroups that you can always point to as sort of general constructions that work for every arbitrary, that make sense for any arbitrary group? For example, only rotations makes no sense if you're in a context where there is nothing rotating. There's no triangle, there's no pentagon. So only rotations is a very specific example of a subgroup that's specific to that example. So now I want to do some kinds of examples which are like so general they're boring. Okay, but they're important though. It's important to know what's generally true so you don't reinvent the wheel every single time you find a specific example. So let's do abstract garbage now. Okay, so here's an example of a subgroup. It's called the center. The center of a group. Okay, so this is called the center of a group. It's interesting. Interesting name. Okay, so it's denoted ZG. Okay, some people denote it CG. Okay, I don't know which one the book does. I think maybe CG. Not sure. All right, but I prepare you for lots of notation later when I'm not your professor. Okay, so here's what it is. Definition. The center of a group G, denoted ZG, let's just go with Z, okay, is the following set. It's the set of elements in the group which commutes with every other element in the group, such that G times H equals H times G for any element in the group. Okay, let me try to situate you correctly in this, tell you where this example comes from. Before we do a little baby proof, very baby proof, before we do this, prove anything, let's say where this example comes from. So here's a little comment, remark. Here's a comment I want to make. It will turn out that we have great confidence, great ability, great clarity in the presence of an abelian group. We'll have way more to say about abelian groups. Commutative groups, we'll be able to list all of the finite commutative groups in the world. Just list them. Here's a list. Oh, you got a commutative finite abelian group? Oh, here it is. It's in here somewhere. Which one? Oh, we'll just tease it out a little bit. Okay, so we'll have perfect clarity on abelian situations. General theme. Okay, so it'll turn out that abelian groups are super friendly, are super understandable. And what tends to happen in this subject is certain definitions and constructions are created or observed, which try to measure how non-abelian is a given group. Okay? And this center is one such little measurement or little organ you can check in the group to see how far is this thing from being dream situation abelian. That's the kind of framework that we're kind of the theme we're introducing here. Okay? So here's a subset right now. ZG. It's the set of elements in the group that commutes with everything. So if you ever write it in a product, you can freely swap its order. Okay? These special elements in the group, in this group, which commute with everything. The most abelian elements, so to speak. Yeah. They're, we circle them and we give it a name, ZG. Now here's the little baby theorem. Baby theorem? They're baby theorem because they're not very hard, these first little observations, baby theorem. The center of a group is a subgroup. Okay. All right, for example, I'll show you closure, e.g. closure. Sure. Let's check closure. All right. If G1 and G2 are two elements in closure, meaning if you give a mouse a muffin thing or whatever. If G1 and G2 are two elements in this center, then for any element in the group, check this out. G1, G2 times H equals associativity, something, something, equals G2 is in Z, equals G1 times HG2. So these two are equal because G2 is in the center. Okay? Okay, and then as, right? Okay? And then G1 is in the center by hypothesis, right? Equals G1 is in the center. Equals H times G1, G2. As. All right? So, indeed, this element also commutes with everything. H was everything. All right? Fantastic. All right, so that's closure. All right? Great. Okay, so, obviously identity is in there. Identity commutes with everything. And now, for my students, check inverse. Okay. Oh, hello, Professor Peter. Awesome. Welcome. Lots of galaxy brains in the chat today. Okay. So, if my students have no questions about this, I will continue with some other related types of examples. So, related examples. Similarly. Okay. There's a type of construction in group theory called centralizer. Okay, the context is this. Suppose A is some element that you are very, very interested in a group. That's the context. This one had no context. Center is just, of the group is just, boom, born. But the next one is like, the context is, suppose you have a particular element in a group. So suppose A is an element in a group, then the centralizer of A is denoted. Okay, I'm gonna use some notation right now. I'm gonna actually use C of A this time. I don't know if this is what the book uses. I'll switch it later, but this is definitely the word, centralizer of A. So the centralizer of an element, it's just another type of example I want to show you. Denoted this is the following set. It's the set of elements in the group which commute with A. You see, this is kind of like, go back to my weird comment about how would you start measuring the non-commutativity of a situation. This time, this is like, how would you measure the non-commutativity of an element? Well, you'd go around and you'd ask, like, which elements does this one commute with? And then you'd circle those and just say, like, look, this is your commutativity-ness. Okay, well, yeah, here's a subset. And the point is that this natural subset, which you'd sort of circle if you're looking at how commutative is this element A, that thing is not just a random subset. Great news, celebration, it's a subgroup. That's the little baby theorem. Here's baby theorem. Okay. All right, so centralizer of A is a subgroup. Okay, so good. Okay, so closure is easier. Closure is the same. But what I want to do is practice with my students. So what I want to do, I want to practice to have student participation or chat. And I want to try something more fun. Okay, so the fact that two elements in the centralizer multiply to another element in the centralizer of A is simple. But how about inverse? Let's try inversion. Let's try to show students that if G is in the centralizer of A, then so is G inverse. Okay, so this might be tricky for my students, but I want to sort of puzzle my way through it so that we get practice teasing out an argument in group theory. All right, so we're going to practice. We're going to try to show that if you have an element in the centralizer, then its inverse is also in the centralizer. Okay, so let's go to general. I'll just go into this voice channel if anyone wants to join. And now people in chat can also try this. Try to tease out the proof that inverses exist in the centralizer, or stay within the centralizer. Okay, so how many of my students are awake? I don't know, actually 4 of them look online right now. Does anyone have any ideas they want to throw out? Wow. Okay. Let's write what Ryan Looney just busted out. Ryan Looney, I think, yeah, Ryan Looney, or RDL, I believe, just busted this out. Okay. All right, here we go. Look at this beautiful thing that came out. Okay, if G is in G, okay, if G is in centralizer of A, then A times G equals G times A. But that implies, okay, let's see. That implies, let me make, I'm just reading it right now. I assume it's right because it came out with such force. Okay. That implies by multiplying on the left and right by G inverse, absolutely, right? I mean, I just multiplied left and right. Left and right on left and right. Good, by G inverse. So this is, look at that, associativity. These two will cancel, and so you get G inverse A equals, cancel, A G inverse. Okay, 100%. There you go. So that's the i.e. G inverse is also in the centralizer. All right, so that was a brilliant proof. Wonderful, well done, RDL. Yeah. Okay. So, but students, you should learn from this the flavor of general group theory in the beginning where we are right now. There's like a couple bags of tricks. So there's like a couple tricks to try. You sort of start with equality. So here's one. Here's RDL trick. You're going to be given, your hypothesis will be like some expression equals some other expression, whatever. Just abstract nonsense, okay? Here's RDL principle number 1. Do something natural. Like, natural means like, usually all you're given is some symbols like G and A. That's all you have to play with. You don't have, oh, rotate by 240. No, you have G and you have an A. So natural means cooked up from G and A. Do something natural, like multiply something cooked up from G and A on both sides. Natural. So this means vaguely involving the initial puzzle pieces. Do something natural to both sides. And hopefully try to situate inverses next to original elements. Okay, that's this part. This little part. Okay? So this is something to try with RDL principle, general principle. Do something natural to both sides. Part of that principle, here's another part. I mean, I put it separately, but it's not really separate. Remember that you can also invert both sides. You can also do that. Invert both sides. Sometimes that gets you, in combination with RDL, it gets you places. But you know, for right now, these are the kinds of moves you'll do. In this case, we multiplied by G inverse and G inverse again on both sides of the expression. A lot of times, another trick that comes up a lot is multiply by G inverse and then blah, a star. And then G, only G on the other side. This little move, this kind of a manipulation also happens sometimes in arguments, okay? So RDLs was like with an inverse on both of these G's, that got us where we needed to go. But sometimes it's just this kind of a move. And this kind of a move where you multiply by an inverse of an element on the left or on one side and it on the other side, like this, is called conjugation. So just keep a bag of tricks kind of in your mind, a toolkit for how abstract algebra arguments typically go at this very early level, especially like checking if something's a group and so on. Awesome. Multiplying by identity could also be a trick. Yeah, when you write identity as like something times its inverse. Yeah, that can also be a trick, Galvabart. Absolutely. Okay. I don't know if that's what you meant, but that's what I interpreted that comment as. But yes, 100%. The bag of tricks isn't a well-defined thing. It's just something to keep an eye on. Okay, so centralizers. Okay, so let's just make some obvious observations. Obviously, G is abelian if and only if the center of G is the whole group. This is obvious by definition. Everything commutes with everything else. Okay? G is abelian if and only if the centralizer of an element is the whole group for any element in the group. Okay? So it's in these sort of senses that the centralizers or center of a group measures the abelianness. You could say, like, if the center of a group is only the identity element, is trivial, like E. So you can, in your mind, you can vaguely think, if the center of a group is just the identity element, it's kind of like it's, in this sense, further on the other extreme, far from being abelian. Then G is far from being abelian. Far according to this discussion. All right, good. One day we'll see another type of group called the commutator of a group, and it'll also kind of measure how abelian a group is. It'll be measured in a different way, and we just sort of have to collect these types of measurements. Okay, so the last thing I want to say about the center of the group G is something that might not make sense right now, but it's very important that you understand this principle. Okay, so this center, the center of a group is an intrinsic part of a group. So that's a new theme I want to introduce. The center, or Z of G, whatever I've been saying, Z of G, center, the center of a group is an intrinsic subgroup of a group. Okay, this might make no sense to you, and some people will think that that's not a precise statement. Why are you using this language? But there's something intrinsic to the center that's not true or common to just any other subgroup of a given group. Okay, so what I mean by this is I'm going to give you an analogy. And this analogy is trying to get you to the notion of something that's intrinsic construction in group theory versus something that's ad hoc and very special to a particular example. So here's an analogy. If you have something like an isosceles triangle, okay? And it's just the triangle, okay? It's just a triangle. Here's what I mean vaguely by intrinsic. Okay, so if you circle this vertex, this point on the isosceles triangle is not an intrinsic point on the isosceles triangle. This vertex is not really intrinsic. here's what I mean. You take the triangle and you put it in your backyard, okay? And we're in Oklahoma, so like a tornado comes the next day, picks up the triangle, moves it around, yeah? It goes flapping in the wind and it comes back down, all right? Okay. You come back to the triangle, you will not know which of these two dots, which of those two you were looking at the day before. You will not be able to distinguish between the left-hand dot and the right-hand dot, okay? That's what I mean by these two parts of the triangle are not intrinsically identifiable in the triangle. Okay, what's intrinsic to the isosceles triangle is something like the axis. This middle line is intrinsic to the isosceles triangle. It's something that even if a tornado came and flipped the triangle around a lot and then it settled down, even tomorrow you'd be able to come back and identify which line you were talking about. There's something intrinsic about that part of the object, and there's something less intrinsic, not always identifiable, about just left vertex or right vertex. It's in this kind of sense that the center of a group is intrinsic to the group. It is part of the core anatomy of the group. Anybody who ever comes back to that group will always be able to identify that this is the center of the group. It doesn't involve doing some unnatural picking and choosing winners and losers in the group. So that's the kind of thing you're looking out for in the abstract theory. Intrinsic constructions of subgroups in a group, those are like organs in a body, and we'll sort of gain an understanding of a group by looking at these vital signs, these intrinsic pieces of a group, and situating them in our mind based on the relative sizes of these pieces. Okay, awesome. So next I had on the agenda Smash Time Fools? Absolutely. The subgroup, which is just the identity, is intrinsic to a given group, as is the whole group. Yes, absolutely. Fantastic. Okay, so there's a lot of... okay, next. So what was on our agenda for the end of class? It was just to come back to Earth. I mean, what was that? We just got flipped around by a tornado, and now it's time to come back to Earth with this ongoing game. How many groups do we know? Let's go list them. I'm gonna go fast. I'm gonna list as many that we know, that we've seen so far. Okay. Trivial group. 1. Under multiplication. Okay. 1 minus 1. Multiplication. Z mod 2z. 0. 1. Under adding. Modular adding. Mod 2 adding. Z mod nz. Or mod n adding. Okay, we've seen these. Dihedral group. Dn. Rotations. Flips of a perfect regular n-gon. Okay, in here, let's call it Rn. Rotations only. I mean, I'm just spitballing here. Spitballing. Oh my god, UB Prof has a perfect diagram of the dihedral group, D3. Thank you. That really makes it clear what we're studying. I was unclear about what are we doing, but now UB Prof comes in and with pedagogical mastery shows now my students get it. You know, now they get it. Awesome. Thanks for the Dorito. Okay, so we got this, we got that, we've got GLN. Real matrices. You got all kinds. Oh, you got C cross with multiplication. Non-zero complex numbers. There's no rhyme or reason. I'm just throwing out all kinds of groups. Complex numbers with multiplication. Okay. Here's something. I'll call it mu n. The complex numbers which are the nth roots of unity. So this is a subgroup. Let me write it another way. It's e to the I times 2 pi over n times k. 2 pi, multiples of angle 2 pi over n. Okay, we got all kinds. Oh my god, so many groups. This is incredible. Okay, one thing that's kind of strange about this list that many of you might start to object to. Students, you can go. This is just me trying to make a list. You make your list as big as you can. Keep adding to it. Keep asking, do I understand this group? What's the center of this group? Blah, 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 blah. But one thing I want to sort of point out that we're going to move to next week is the following. That some students might get the distinct sense that this list has a lot of repetition. There seems to be a lot of repetition in this list. I don't know if you have this sense. Ask yourself, students, if you feel this way, that this group, for example, and this group, that these in some sense are repeated. This is like a repeated entry. This is some sense that one has. You might also get the sense that this group and only the rotations, maybe this is a repetition, repeated entry. You might get the sense also that mu n and z mod nz and rn, the rotations of angle n, that this is also repeated. So we'll make bigger and bigger lists saying what's new groups that appear to be new, but okay, what I want to just leave with, end with, what do we mean by repeated entry? Exactly. Because if you look at it, they are not literally the same. One of them is a bunch of brackets with numbers in them, and you do some bracket math called mod n adding. The other one involves you have to have a regular n-gon in front of your face, and you have to be rotating it. That's Rn. The other one is you need to be looking at complex numbers. Certain ones, the ones that whose nth power is 1, nth roots of unity. Only those. Complex numbers. 0, 1, 2, bracket n minus 1, that's not a complex number. So what do we mean by repeated? And that's a topic that's coming up very soon. It's the concept of an isomorphism between two groups. All right. So that's the little in your list of groups, start asking which groups are spiritually the same as each other, though not literally the same. Okay. Galvabart, yeah, great. Absolutely. Okay, so that's enough for today's verbal diarrhea from me. I'll move to just addressing some questions in class, or from the class, or from the curious people in chat. Not in the class. Okay, spicy nacho gang. Okay, so there's some intense debate on what kind of Dorito is the best. Professor Peter, welcome. Peter is a moderator, so you must behave in their presence. As is Smash Time Fools. Oh yes, that's right. Smash Time Fools wanted me to juggle, so let's juggle. Fools. I'll keep an eye on any... Oh, Arbitrary needs some shungite. Hey, but congratulations on the interview, Arbitrary. Here's your shungite blessing. And I hope this eliminates all the 5G interference in your life, Arbitrary. Besides C star, what are some other continuous groups to think about? Circle rotations. Hey, I don't know. Obviously, I don't think you're asking, but thank you, UB Math Prof. Yeah, here's another group. Sorry, let's just add to this list. Okay, here's UB Math Prof's Math Proof's suggestion. Rotation. These complex numbers. These complex numbers, where theta is in 0 to 2 pi. Okay, yes, these complex, or if you'd like, so that's one thing, a set of complex numbers. That forms a subgroup, okay? And it looks like the unit circle in the complex plane. These are the unit circle elements. Okay, that's one, yes. Another entry could have been these matrices, and only these matrices. Inside the space of 2 by 2 matrices. Again, theta is an angle from 0 to 2 pi. Okay? This group of matrices, this collection of matrices is a subgroup of GL2R, and it's the set of rotations of around the origin. When you think of a matrix as a linear transformation, this is a set of rotations around 0, around the origin, viewed as a linear transformation. Okay, so yes. And this is, someone asked in the Discord last week, how do you make the circle into a group? The circle is just the set of angles, theta. And here's your group, here's a group structure on the circle, or the unit circle. Unit circle has this natural group structure called adding angles. Okay, recorder plus juggling. I don't know if they commute, but one could try to see. Why GL2? It's just an old phrase, general linear group. This is a 2-dimensional vector space over this field, over the real numbers. So it's a set of linear transformations of a 2-dimensional vector space into itself, and it's general linear transformations, not special ones, not rotations only or only. Yeah, not determinant one, nothing special, just general, the whole list. Center of a mass of a cloud of points? No, I don't think. No, it's not the same. It's Yeah, I actually don't know why the exact word center was used. I can make up some BS stories that make sense to me, but a lot of this stuff was made by really old people, and they used the language kind of better than we do now, and so I don't even know why they use certain words. Pandemic, SLP, pandemic. SL. I don't know why pandemic showed up in your answer, math prof. I don't get it. But anyway, we gotta get Smash Time Fools request. Okay, so they're asking me to try to play the recorder. I have a it was the trivial song on One Element. Sorry about that. I can't. It'll be difficult for me to change notes while I'm juggling, but there you go. It's possible. Anything's possible. Smash Time Fools. If you just put your mind to it. Awesome. All right. What else? What other questions? Oh, pandemic watch. Oh, I get it. I was like, why is the pandemic related to SLN and PSL? I don't get it. But yeah, thanks. That makes more sense. Okay. Oh, octaves? I could probably do an octave. Yeah. I suppose there can be rotations of higher dimensional things, shapes. Yes. In fact, every shape has a group of symmetries. Now, some shapes are less symmetric, unfortunately, than others. Their group will just be the identity element, sadly. But you can have some really brilliant shapes, like the platonic solids, maybe, is what you've got in mind, Pandemic Watch. Icosahedron, I see you noticed. Yeah. The icosahedron, the group of rotations in space that keep the icosahedron within itself, is a absolutely stunning and important group called A5. It has 60 elements, and it plays an absolutely important historical role in group theory. But we haven't gotten to A5 yet, because I need to teach you what teach my students what S5 is first, and then we'll know what A5 is after that. It's S5 divided by 2, so to speak. Okay, anyway. I've heard commutator and conjugate with respect to... Yep! Yeah, Galvin-Bart. No, that's the literal same exact wording. That's not like a... There's no surprise that the Rubik's Cube, the solution of the Rubik's Cube can be phrased group theoretically. That's like, yes. We are transforming this cube in certain invertible ways. This way can be undone, but this one can be this action can be undone with that action, etc. So there's a little group underlying the Rubik's Cube. It's not a little group, it's a big group. And that's completely the same word. All right. Let's see, what else do these people... Besides C star, yes. Yeah. Okay, good. I think I've dealt with everybody. Zentrum? Z? Oh yeah, maybe. Yeah. I bet you it is German. Galvabart. Yeah. I bet you it is. Yeah. Um. Okay. Okay. So, as you all know, I have a highly annoying Calc 2 uh, uh, class. They're just full of degenerates. They're not gonna watch this. So I gotta go make up some little activities, little fun little things for them. Keep them happy. We're gonna be just integrating some stuff just to make them jump through hoops and problem solve. Basically, that's what we're doing. I'm just making up integrals so that they learn how to navigate some problems using a well-defined little list of techniques. Don't tell them that though. We'll say that it's very important that they know how to integrate sine 4x times cosine of 5x. Like that's how they'll balance their checkbooks. We'll just say that. They'll believe it. They just believe everything. So, but it's actually just mental exercise, raw mental exercise, but that's not good enough for them. So I gotta make up these little kind of stupid puzzles, and and I also have to cram some food in my mouth in the middle, all at once. So it's kind of I gotta go. Let's see who's out there. So dump you guys. Okay, raid. Gath. Oh, Gath is out there. Gath. Okay, Gath, are you accepting raids? Hell no. Okay, so that's good. That's good. Massive rejection. Who else is out there? You guys have any she's teaching. Okay. Prof. Melko. Canonical choice. Let's see. You guys want to make some money? You guys want to learn how to make money? Or lose all your money? I don't know which one it is yet. I haven't figured that out. But, yeah, here, let me just send you to lose some money. Okay, everyone, just, here, go to this. Yeah, oh yeah. Thanks for coming, Galvabart. Thanks, everyone. Tropical Geek, all you folks. Yeah, thanks, Pandemic, 2Stock, buy one, get 16, ASCII only. Thanks, Yarrow Cray, Third Eye Lazy, everybody. Thanks. Okay, now, yeah, come back and one day we'll explore A5 together again. Oh yeah, no, no problem, UV Math Prof. Thanks for the league groups. Okay, all right. All right, so here, go, learn how to gamble all your money away. All right, see ya, Arbitrary. All right, go gamble all your money away. See ya. Okay. Oh my God! Finally, I'm done with this garbage. Tensor products.